Yes. So in this video what I am going to do is I am going to give a basic introduction to differential equations, right? So I am not going to define what is meant by ordinary differential equations, what is meant by partial differential equation, but rather I will make you to visualize what is meant by ODE, that is ordinary differential equation, and what is meant by partial differential equation, right? So because these two topics are very important in any exam point of view. So in UPSC there will be around 70 to 80 marks from differential equations, that is from ODE and as well as PDE, right? So far what we are did in our channel is I have posted around more than 167 videos on UPSC maths optional, and out of 167 I have posted videos for linear algebra and complex analysis, abstract algebra, calculus and real analysis, right? So we have solved all previous question papers on real analysis. So in the description I will give a link for all playlists, right? So if you haven't watched that video, please watch that video also. So this video, after this video what I am going to do is I am going to start differential equations, right? So that is why I make this setup, because this concept is very important, right? So rather than mug up in the definition, we first need to memorize the concept, right? First we need to understand the concept, then only we can solve any problem. So to understand ordinary differential equation, first what we need to know is, first we need to know what is meant by derivative, right? So if we know derivative, we can talk about ordinary differential equation, and if I know partial derivative, I can talk about partial differential equation. So first we need to know what is meant by derivative, then only we can talk about ODE, right? Then I need to know what is meant by partial derivative, then only I can talk about partial differential equation. So in this video what I am going to do is, first I am going to explain what is meant by derivative, right? And then I am going to explain what is meant by partial derivative. That is what I am going to do in this video, and I am not going to define let f be a function on blah blah blah, not I am going to define like this. I am just going to give intuitively what geometrically means what is meant by derivative and what is meant by partial derivative, right? So first we will understand what is meant by derivative, right? So whenever I say derivative, it is a function of single variable, and whenever if I say partial derivative, it is a function of multivariable, right? That is more than one variable. So first we will restrict our case only to a function of single variable, that is y is equal to f of x. Now we will discuss what is meant by derivative now, right? Yeah. Yes. So let us say, so this is our R2 plane, right? This is our R2 plane. So let us say we have a function like this. Let us say we have a function like this. So this is our function y is equal to f of x. So this is our function y is equal to f of x, and this is our x axis and this is our y axis, right? So suppose if I need to find the derivative at this point, right? I need to find the derivative at this point. So this is our x. Now I need to find f dash of x, right? So given a function, you can find f dash of x using lot of formulas, but I am going to explain only geometrically. So what derivative means is that it is the slope of a tangent line, right? The slope of a tangent line is called the derivative. Now that is, this is our f dash of x. So this, that is, we need to find the slope for this line, right? So we need to find the slope for this line and the slope for this line. So this is a tangent line, right? Tangent, you know what's meant by tangent? A line that touches the curve at only one point is called a tangent line. So this is our f dash of x. So we need to find the slope for this line. But what the problem is, for this line we have only one point that lies in this curve, right? So to find the slope for a line we need 2 points, right? So if I have 2 points, I can find the slope using the formula y2 minus y1 divided by x2 minus x1. But what the problem is, we in this line, in this curve, we have only one point here. So we need some other point, then only I can talk about slope of a line, right? Because I need 2 points to find the slope of a line. Now what I am going to do is, I am going to take some arbitrary point, right? So let this point be our x plus h. So this is x and let this distance be h. So this distance is h, right? So what this point will be? This is x plus h. Now as a function, this is a value of x at f, right? This is a value of f of x at x is equal to x, and what will be here? This is f of x plus h, right? This is a function value. So this is x plus h, and the curve, the function value is f of x plus h, and here it is x, and function value is f of x. So far what I did is I have taken some arbitrary point x plus h. So in a curve or in a shape, when we connect 2 points, we call that as a secant line, right? So whenever we are connecting 2 points in a curve or a plane, we call that line to be a secant line. So what I am going to do is I am going to make a secant line from this point to this point, right? That is what I am doing now, right? So this is our secant line now. This is our secant line. This is our tangent line, right? We need to find the slope for this tangent line. So what I did is I have taken a secant line. Now what I am going to do is I am going to find the slope for secant line, right? I can find slope. Why? Because I have 2 points in this curve, this point and this point. So what is the slope formula for a line? It is, our slope will be the slope of secant line, right? Slope of secant line is y2 minus y1 divided by x2 minus x1. This is the slope for secant line. So what is our y2 now? It is f of x plus h. And what is our y1? It is f of x. And what is our x2? It is x plus h. And what is our x1? It is x, right? So when I apply that, we will have f of x plus h minus f of x divided by x plus h minus x, right? So this x will get cancelled. So we have only f of x plus h minus f of x divided by h. Remember, this is the slope for secant line. But what is our aim? We need to find the slope for tangent line, right? Yeah. So far what we did is we have found the slope for secant line. Now how can I find the slope for tangent line? That is the main objective now. So I have chosen arbitrary h, and this will be x plus h. So what will happen if I take h smaller than this? So let us take, instead of this big h, what I am going to do is I am going to make a point here. So this is our new h now, and this is x plus h. So what will be the function value? Our function value is here, which is f of x plus h. Now what will be the secant line? Secant line will be somewhere around here. This is our new secant line. If I reduce the value of h, that is, if I am just reducing the value of h, right? I am just reducing the distance of h from x. So what will happen if I choose h here, if I choose x plus h here? So first I have kept this distance for h, and I kept this distance for h, and I kept now this is the distance now. So where will be our f of x plus h? Here will be f of x plus h, and what will be my secant line? So I have to connect this point and this point. So we will have a secant line like this. Now you can see the difference between this line and this line. So as h approaching smaller, that is, when the distance between x and x plus h, as h becomes smaller, what you can see is this secant line is approaching the tangent line, right? So this secant line is approaching the tangent line. You can see that this line and this line is far closer than this line and this line. Why? Because our h is small here. So what will happen if I take x plus h here, more closer to x, then as h tends to 0, you can see this secant line will be same as tangent line, right? So this is the slope of secant line. So we can find the slope of tangent line if limit s tends to 0. If I make the distance of h tends to 0, we can see as smaller, the secant line and the tangent line will become closer. So at some stage, as s tends to 0, this line will be same as this line, right? So as s tends to 0, this will be a slope of this tangent line, and I'm going to call that as f dash of x. So this is what derivative geometrically mean, right? So this is the formula, limit s tends to 0, f of x plus h minus f of x by h. So you know what's the derivative now. So a equation involving derivative is called ordinary differential equation. That's it, right? So a equation involving derivative. For example, d square y by dx square plus dy by dx is equal to something. You can see this equation involves an equation of derivatives, not single variable. So an equation involving a derivative of single variable is called the ordinary differential equation, right? Now we will move on to partial derivative. So what is meant by partial derivative? Then we will define what is meant by partial differential equation. Yes. So now we will define what is meant by partial derivative, right? So whenever if I say partial derivative, it is a function of two variables. So let us restrict our case to a function of two variables. That is, z is a function of x comma y, right? Z is a function of x comma y. So you can see this is our x-axis, this is our y-axis, and this is our z-axis, right? Yeah. So can I talk about a tangent line at a point here? That is the question now. So can I talk about a tangent line at a point? So for example, so let us take a point. Let us take a point somewhere around here. So this is our point x naught comma y naught, right? This is our point x naught comma y naught. That is, so at this is our x naught and this is our y naught, right? So this is our point x naught comma y naught, and where will be the function value? Let us say our function value is here. Let us say this is a value, that is our f of x naught comma y naught is somewhere around here, right? So can I talk about the tangent line at this point? It is not possible, right? Because you can see we can draw tangent line in any direction. So the direction is not clear, right? So we can, in a function of single variable, we can draw only one tangent line for a particular point. But here it is a function of two variables, right? So what is not possible is we cannot draw a tangent line. So remember tangent line to this point because the direction is not clear, right? So instead, what we can draw is we can draw a tangent plane, right? So whenever I am talking about function of two variable, we should say it is a tangent plane, right? So I have taken a smooth function. Z is a smooth function, right? The smooth function means the function has no sharp edge, right? So let us say it is a blanket and it has no sharp edge, right? Let us assume that there is some blanket and the blanket has no sharp edge, right? So if there is no sharp edge, we cannot talk about derivative, right? That is already explained in calculus playlist. So let us assume the function is smooth, and for every point, what we can do is we can talk about tangent plane, right? So for every point, we can talk about. So let us assume this is a plane. This is a plane. So for every point, what I can do? I can talk about a tangent plane, right? So this is a plane, and for every surface, so this is our blanket now. So what I can do? I can draw a tangent plane here. So what I can do is I can draw a tangent plane for every point. I cannot draw a tangent line, but instead what I can do is I can draw a tangent plane for every point. So our tangent plane will be like this when if it has a maximum point, right? So if it has a maximum point, we know in single variable, if I have maximum, then the derivative will be parallel to x-axis. So same case here, our tangent plane will be here, like this, if it has a maximum point, right? Suppose the curve is maximum here, the tangent plane will be right here. If not, a tangent plane will be somewhere around here. So we can talk about tangent plane for every point for a function of two variables. So instead, what we can define here is we can talk about a tangent plane, right? That is what we are going to do now. So for that, what I am going to do is I am going to fix x naught, right? I am going to fix x naught and I am going to vary y naught, right? I am going to fix x naught and I am going to vary y naught. that is our x naught is fixed and y naught is varying. So let us say our function value for this point is somewhere around here, right? And let us say our function value for this point is somewhere around here, and let us say this is our new function, right? So what I'm doing is I'm fixing x naught and I'm finding and I'm varying y naught, that is x naught comma y1, x naught comma y2, and I'm plotting the function value. So let us say this is our graph, right? So this is obtained by fixing x naught and altering the y naught, changing y naught. Now it is possible for us to speak about a tangent line at this point. Why? Because we are restricting our case to a single variable only, because we have fixed x naught and we are varying only y naught. So what will be the tangent line for this plane? Let us say this is our graph now. So what will be the tangent line? This will be the tangent line, right? So this tangent line is obtained. This tangent line is obtained by fixing x naught and varying y naught, right? And I'm varying y naught. Now what I'm going to do is I'm going to fix y naught and I'm going to vary x naught, right? So I'm fixing this and I'm varying x naught. So let us say our function value is somewhere around here. So this is our new function now, right? So this curve is obtained by fixing y naught and changing x naught. So what will be the tangent line for this point? It will be around here, right? So there is a tangent line obtained by fixing x naught, and this is fixed. X naught is fixed and I varied y, and here x naught is fixed, y is varied, and for this y naught is fixed, x is varied, right? So I have two lines, right? I have two tangent lines. What you can say about that? It is a plane, right? It is a plane. So whenever I have two lines intersect, it is a plane, right? So as long as it is not parallel, then the intersection of two lines will be a plane, right? So what we found is, so first what we did is, so let us say this is our surface now. This is our surface. So what we did is, so let us assume this surface to be my head, right? So first what we did is, we have taken some arbitrary point here, right? So this is from x, this is from y, this is our x naught comma y naught. So what will be the function value? Let us say function value is somewhere around here. So this is our f of x naught comma y naught, right? So what we are required to find? We are required to find a tangent plane for this point. So we are required to find the tangent plane for f of x naught comma y naught. So for that what we did? First we fixed x naught and I varied y, right? And I varied y. So I obtained a tangent line like this, right? So I obtained a tangent line like this. Then I fixed y naught and I varied x and I obtained a tangent line like this. So what I got is, so first I fixed x naught and I varied y, I obtained a tangent line like this. Then I fixed y naught and I varied x naught, then I obtained a tangent like this. So you can see this is a plane, right? So what we have just obtained is, we have just found a tangent plane for this point, right? So what we did is, we have found a tangent plane for this point, which is our f of x naught comma y naught, right? So that is what partial derivative means. So here what we did, what is this line? This is x naught is fixed and I am varying y. So I'm going to call this tangent line as partial derivative of f with respect to y, because y is varying, right? So this is our dou f by dou y. This is our dou f by dou y. So how I obtained this? This is obtained by fixing y naught and x naught is varying, right? So I'm going to call this line as dou f by dou x, right? So partial derivative with respect to y and partial derivative with respect to x. So this is what partial derivative means, right? So So first you have to understand the concepts, then you can clear. So I have solved many problems using dou f by dou x and dou f by dou y, right? So in the previous video also I have solved a problem. They have given a function of two variable and they asked us to find the and they asked to show that partial derivative exists at 0, 0. So what we are doing is I have given a formula that fx of x, y will be f of, let us write it here. So in that video I have given a formula like fx of x, y will be limit s tends to 0 f of x plus h, y minus f of x, y divided by h. This is the formula I have given now, right? Because why? I am varying y, right? So we are going to call this as a partial derivative with respect to x and partial derivative with respect to y. This is what we are going to do. And an equation involving partial derivative is called partial differential equation, right? So here there is a function of x, y. Suppose if I have a function, if I have an equation like dou z by dou x plus dou z by dou y, you can see it involves partial derivative. So we will call this as a partial derivative, partial differential equations, right? So an equation involving derivative is called differential equation, and equation involving a partial derivative is called partial differential equation. So the next video what we will do is we will solve how to solve a differential equation. So first we will finish ODE and then we will move on to PDE, right? So this is what I need, this is what you also need to. You just want to understand the geometrical idea behind this, right? So anyone can solve problem, right? So understanding the concept is very important. So I hope you enjoy this video. That's it. We'll see in the next video. Goodbye. Thank you.